morning. I hope you woke up, prepared some coffee, and are ready for this talk. Today, we will talk about performance issues in production and how to react to these production incidents. This is an essential slide with very long sentences on it. The main point is everything you do in production is your sole decision, and neither my employee nor I am responsible for your troubles. Ideally, you have to double check everything you hear at conferences before implementing it in your production infrastructure. Okay, so who am I? Currently, I work as a software engineer at Platica at Infra Department. Also, as I was already saying, I contribute to a few open source projects. Last few months, to rental application server. I'm also a massive fan of scientific method and try to make my judgments scientifically, and this will solely affect our talk. You can reach me on Telegram by my nickname, Riodont. We have a lot to discuss today. Most important, motivation. Why should we even spend time on this talk? What problem do we solve? And why do we care about this? We also should get onto the common ground in terms of terminology. I will specify what I call system performance and will clarify some terms. It is essential to mention what methodologies or patterns people usually use when they encounter performance issues in production and why they're often ineffective and lead to erroneous results. If we want to know how to do something right, it is good to know what definitely not to do. After that, we will discuss a methodology that I recommend following to locate and fix performance issues with real-life example. I found this great meme at XKCD platform, and I believe it will help me describe talk motivation precisely. I have worked with multiple teams, domains, and companies, and most of the time, I have seen people making the same mistakes when encountering performance issues. When trying to achieve goal X, they chaotically move from one hypothesis to another. They blame third party, blame another teams, blame frameworks, databases, etc. After a lot of struggling, Googling, asking questions on Stack Overflow, random tuning of the GVM parameters or any other hyperparameters of the system, like tuning Linux flags, etc. People tend to create some new problems, believe that they resolve the issue, or try to convince their managers that problem is like fundamental and unsolvable at all. This is ineffective and not the best of engineer. When developing a system, we think of functional and non-functional requirements, create architecture, and plan our work. We are working by methodology, an ordered list of steps that we should do to complete the task. I ask myself why resolving performance issues should differ fundamentally. We definitely should cultivate methodology, guidelines, engineering culture for resolving performance issues to fix stuff effectively, consistently, and estimate our work like any other activity of software engineer. System performance is actually very extensive topic, so we should limit the scope of the discussion. We will not discuss any tools such as tracers, profilers, monitoring, observational tools, because we will need like extra hour for that. We will not discuss benchmarks. Although correct benchmarking is essential in system performance study, in performance engineering, we will need a whole separate talk about types, KVs, theory, and practice behind the benchmarks, and we don't have time for that. We will not discuss operating systems, file system, memory subsystems, garbage collectors, clouds, KVs, because we don't have time for that. And also, we will limit the scope of the discussion and Q&A only to GVM-based projects. Okay. So let's move with the definitions and talk agreements. So, in my opinion, system performance is a measure of how well the system performs under applied load. Performance itself can be measured by observing the states of system components, both software and hardware. On the other side, performance engineering is a set of techniques used to ensure the required level of system performance, described as a non-functional requirement for a system architecture, is achieved. Performance engineers' typical activities are setting up, observation, and monitoring system components, profiling system components against specific or targeted important workloads in order to find bottlenecks, hypothesizing about performance issues' root causes, validating theories, and fixing bottlenecks. Most of the time, it involves deep dive through the system stack, from application down to hardware, so it is crucial to understand your underlying stack and what tools can be applied to each system to fix issues effectively. Some of the metrics are the object of misinterpretation, and I want to use some talk time because they're essential in talk context. The most common one is latency versus response time. Once again, latency is a connection latency, the time that server needs to receive a package of data. We are most interested in the time spent on sending, processing, and receiving data, that is response time. Response time is a key metric which we will use during the talk. The next pair of related terms are utilization and saturation. Most of you know what utilization is, but not saturation. Utilization is a measurement of how busy some resource was. And saturation is another important metric. It is measurement of worked queue. For example, if some resource like CPU is fully utilized and cannot process any new requests right now, it evades resources. So we have some queued requests. Good side note, if none of your resources are saturated, probably your performance is acceptable. In this section, I will tell you why I think performance is tough and complex. The first and foremost problem in this topic is subjectivity. How do we know if we even have a problem? For example, if I believe our web service, like some crude service, has to respond in 100 milliseconds for 99 percentile of requests to ensure good performance. And my colleague believes that we have to react in 200 milliseconds or less. Who is right and who is wrong and why? Setting up performance goals is really challenging and often not intuitive. Second problem is caused by first, do we know where to stop? I mean, if we optimized some bottleneck and reduced response time by 20%, is it enough to stop or should we continue our work? Performance is tough. Investigating issues is also a challenging topic because it is often unclear where we have to begin searching for the problem. Usually, we only know that we may have a problem somewhere in a system, but nothing specifically. It is hard to understand what components and metrics we can ignore during this investigation and where we should look first and spend more of our time. But this is crucial for estimating time before the fix and spending our time most effectively. The most critical complexity issues are cognitive biases. Cognitive bias, as you may know, makes us think in a certain way, often deviating from rational and logical decision making. Cognitive biases are often a result of our brain attempting to simplify the processing of information. We are consistently getting bombarded with information. Biases help us to unclutter this data and reach decisions with like some speed, with relative speed. However, biases can subtly creep and influence our choices. As human beings, we like to think we are rational, but in reality, we are prone to biases that cause us to think and act irrationally and believe we act rationally. To some extent, every one of us in our lifetime will have exhibited a bias blind spot. According to a lot of researchers from Chicago, University of London, Boston University, today registered about 180 cognitive biases, and list is keep growing, and all of them can impact our rational thinking. Wow, 180. That's a lot to handle. Performance engineer has to be objective, and our goal is to avoid biases at any cost. The second factor is cognitive complexity itself. As the Miller law states, the number of objects an average human can hold in short-term memory is like 7 plus minus 2. We often have to operate in very complex environments and analyze thousands of metrics at hundreds of components at multiple machines in geographically separated data centers during performance analysis. We should understand how to tackle this complexity and not to burn our minds, as Miller law states. And sometimes we can even have multiple issues arise in our system simultaneously, or we can have one problem induced by various causes. Anti-patterns. This is my favorite section actually, because it is about mistakes people make when they try to resolve performance issues by themselves without putting much thinking and planning into this activity and consequences that haunt them afterward. Early blaming. Early blaming is a trendy pattern of action. When something terrible happens, people tend to move responsibility to others without confirming it, avoid solving problem itself, or because they do not believe they can have a problem. People often blame other services such as third parties or neighboring team whose service interacts with others responsible for performance drop because historical trend shows this. For example, if the adjacent team dropped the whole system performance last month, on the following incident, everybody will think that they again did something wrong. Another example is blaming system components that are often underperforming, such as databases, messaging systems, or even Java virtual machine. In my practice, blaming the database is the most common type of this pattern. People think that all their problems are coming from slow MySQL or Oracle DB without verifying this hypothesis. It can be true, but you should verify it. The same goes for frameworks or libraries. Most of the time in the Java world is about Spring or Hibernate. Once again, you have verify every time. Remember, early blaming leads you to biased, subjective, and ineffective investigation in a falsely narrowed scope. You should not rule anything out before you verify it. The streetlight effect, or the drunkard search principle, is an observational bias that occurs when people only search for something that is easiest to look at. Both names refer to a well-known joke. A policeman sees a drunk man searching for something under a streetlight and asks what the drunk has lost. He says he lost his keys, and they both look under the streetlight together. After a few minutes, the policeman asks if he's sure he lost them here, and the drunk replies no, and that he failed to find them in the park. The policeman asks why he is searching here, and the drunk answers, "This is where the light is." So, applying this anti-method or anti-pattern to our topic means that people only use tools and utilities they know and look only at system components metrics they know, and people fix only problems they know how to fix. There is an obvious drawback to this strategy. Imagine how easy it is to miss a lot of performance issues, probably the ones that contribute to performance degradation at most. Remember, performance engineer has to be aware of all system components and as many types of performance issues as possible. But more important is that you should not memorize it. Memorize that there will always be things that you do not know, and you should look for them. Folklore tuning. Folklore tuning is a favorite pattern of mine, and I assume it is the most common one. Have you ever heard how your colleague said to you, "Hey, I recently saw a conference talk of Alexei Shepilov where he showed some great configurations for GVM. Let's tune them on our project." This was the case at all companies I have worked for. People always look on the internet for answers, where people with an unknown level of expertise and interest share their thought and write guides. Well, I mean, not Alexei, he is excellent and I recommend browsing through his blog, but as always, critically. And most of the time, it does not end well for your project. Please remember, each system has a unique tech stack, business processes, workloads, team members, and goals. Magic configurations from Google, Stack Overflow, Bildung may not help you to improve your performance, but can degrade or even cripple your production in runtime. I've been there. Consequences of applying this pattern can be disastrous. Okay, so we discussed what performance is, why it is complex, what you should definitely omit when trying to improve performance. And now it is time I present you a concise way of thinking, a working reasoning model, and a set of guidelines that help me survive through multiple performance disasters. In this chapter, I will try to answer the question how to approach resolving performance issues. But once again, I encourage you to analyze everything I tell you and challenge all this without blind acknowledgement. I present to you key steps that you have to complete in order to fix the performance issue. These are general questions and are project or tech agnostic. First one, do we have a problem? Indeed, it is crucial to understand and clarify with help of non-functional requirements to your project if a newly arrived issue is a problem that has to be solved. You may have a problem, but you should know, should you fix it or not? If we conclude that we indeed have a problem that one should resolve, we should set up a definition of done or acceptance criteria. That would be our stop point, after which we should not spend our time on this task. So we set up our acceptance criteria, and now we have to move to locate causes. Issues location is one of the obscurest places in methodology, and we will spend most of our talk time on that question. And finally, when we located all root causes, we had to prioritize the issue, estimate possible revenue from resolving it, and prepare fix. Fixing itself may vary dramatically from problem to problem. Therefore, I omit this point in the talk. Now let's handle each question separately and in detail. Do we have a problem? Most of the time you will know about performance issues from third party like support. When they come to you asking what is happening with your system, you should know what to ask them to filter only requests that matter to save the time to drink beer with your teammates. So, questions are, why do you think we have a performance issue? This question filters requests that may not be performance related and provide you information about the visible effects of the problem, meaning how users perceive the issue. Ask about recent changes in software, hardware, or applied load. This question can immediately lead you to the reason of performance degradation. Also, it can help you with the short-term fix plan. You just have to revert recent changes. Third question. Can the issuer express problem in terms of metrics? If a person who reports performance issues cannot refer to any metrics and say performance degradation in terms of requests per second, latency, frames per second, or any other metric, that may mean you have no issues at all, or that your observation mechanisms need additional work. Otherwise, you will have concrete advice to acceptance criteria. For example, return latency and RPS to the previous level. Next question is how critical problem is. If your production is down or users are complaining, you should know impact. Answer to this question will help to prioritize your work. If your system is down, then probably it is your number one task in the backlog now to bring it up. Or if some statistics service that no one cares about is underperforming, you may not even need to spend time on it. There is always something that can bring more value. And final question, ask about system configuration and environmental details. The more info you have, the better. Understand where we have problems, staging, pre-production, production, what systems under the load. Ask for service descriptions, service definition documents, high-level definitions, etc. These questions may vary from company to company or even team to team, but this template has served me well a long time as a base questionnaire, from which I developed concrete questionnaires for each system. Methodology. Local stop point. So, we confirmed that we indeed have a problem and we actually need to solve it. Crap. Now it is time for us to set up expectations and stop points of tuning. Where do we stop spending time on an issue? Well, this is business-driven question. You stop when there is no additional value in continuing working. So you should not work if you cannot bring more value. If you have not developed any business criteria or they are unclear, you can move with the provided list. Where do we stop spending time on issue? Well, performance is back on the previous level. It is a perfect option from perspective of like performance. But sometimes it is too expensive, especially if recent software changes with new features introduce performance degradation, and business is not ready to withdraw this fancy feature in order to bring back performance. It is okay to stop when you have found a significant bottleneck and restored something like 60%, 70% of previous performance. Although this solution is not perfect in terms of performance, it is often an acceptable option from a business perspective. If you understand that further investigation costs more than potential gains, it is time to stop. If you spend 3 months tuning an application that brings $200 per month, you are probably burning the company's money because your time costs more. And if you have found a significant bottleneck that can bring more value than the current issue, you should probably take a break from this issue and reprioritize your work. These are common stop points, but the general advice is do things that bring more value. You're doing this to make more money, not for your fun, if you're doing it at work. Okay, so now it is time for us to develop a unified strategy for locating the root causes of issues. We will look at the multi-service system as the most complex type of system from a hierarchical perspective. Keep in mind that you can apply a methodology to monolith solutions as well. So, first step, Identify failing services using the red method and observational tools others. Don't be afraid, I will explain the red method later. First of all, we have to narrow the scope of the search area. We will look at unhealthy services and mark them for further investigation. After we locate unhealthy, aka failing services, we will have to find failing components or resources at that services using the UC method, which I will also explain later. And after locating all failing components, we drill through them with tracers, profilers to find the root cause. If we look through the all failing services and all failing components, we will find all root causes, and after that we can quantify how much each cause contributed to issue or issues performance degradation and plan to fix them. Okay. So, RED is an acronym for request rate, errors, and durations. It is enough to monitor these three types of metrics to judge if the service is healthy. All you have to do is compare the values of these metrics at the time of disaster and compare it to historical data, which we call baseline, when everything was fine, and find a discrepancy between these two data points. If you have found that request rate has dropped, number of errors has grown, or response time has increased, probably something terrible is happening to the service, and it is unhealthy. It is good to look at metrics that observe interaction with other services to ensure that the current service is not failing because of another service, which is called cascade failures, and which can make investigating issues in this complex system very, very hard. UC method I was referring earlier. UC is also an acronym for utilization, saturation, and errors. To find failing component on the system, you must check each resource or component, utilization, saturation, and errors. UC method can be perceived as an analog for the RED method for the concrete computer system. Let's go step by step. You identify your resources like CPU, memory, file system, network devices, applications. Pick them one by one and check their metrics. If you have found some anomalies, proceed with profiling and tracers deep down into components. Otherwise, keep looking at other resources. It is really easy scheme indeed. At this point, it becomes fascinating, varying, and really, really hard. Depending on what RED and UC method resulted for you, you may need to use different tools. If you have found that some applications are causing troubles, go with on CPU, off CPU analysis, thread and lock analysis, application memory analysis. For JVM projects, you can use something like Java Mission Control, Java Flight Recorder, Visual VM for observation, making heap dumps, thread dumps, etc. And if you have found that system resources are responsible for your issues, you may go with BPF utils or default Unix stat and tracing utilities. And starting from here, only your experience and knowledge can help you. Methodology. Here is a general experimenting flow. After you located issue, located root cause, you will have to fix it. I will not tell you how to fix it in generally. I will show you the scheme. You have found the root cause, and now you want to apply some fixes. How can you justify your changes? What is the mechanism of experimentation? First of all, pick a baseline. Document your initial matrix results. Hypothesize a solution and test it with the help of like micro benchmark, macro benchmark, some kind of you should collect new data for your test. Compare results with the baseline. If you have met your acceptance criteria, then you have to stop and document your results. Repeat until you meet your acceptance criteria. And we have an important side notes for experimenting. Do only one change per cycle. Do not twist two knobs at once. If you start mixing different shifts, you will not know what difference helped or was disastrous to your experiment. Okay, we looked at the methodology, and now let's try how this methodology performs at real life example step by step. Let's set up our experiment environment. We have a system with 4 services and 1 database. Pretty easy. Our system is a service with presentations. Customers can enter the platform and view some presentations. We will only look at part of the system responsible for accounting views. Like when client is logging into the platform, he opens presentation and we store his view in the database. We will look only at that part. So we have some presentation service, which is a front-end service clients use for interaction with our system. This presentation service accepts requests from clients when they open a presentation. Presentation service, among other things, has to notify user metrics service via proxy. Proxy service is just a mediator added for clarity of example. And user metrics service is responsible for consuming metrics from other services and storing them into the database. And there is also some business intelligence service that analyzes data from the database using some scheduled jobs. Well, actually, it is a terrible architecture solution, but is both simple and powerful enough to serve as an excellent example to methodology. Well, not systems are perfect, and we have to deal with that in real world. So, you are software engineer responsible for that system. Shame on you. And someday, when you plan to chill out, read some tech blogs, drink a beer, solve a few tickets from your Jira, a second level support engineer call you and tell you that clients are experiencing slacks, company receives a lot of complaints, we start to lose money. What should you do to stop this mess? Panic. Panic sounds reasonable but ineffective. An engineer has to be a cold-blooded creature with a lizard brain. Stop the panic and reason. Actually, this is a good advice for entry-level engineers in general. Calm down and think if you have a problem. Second option, call your team lead. It's probably a good idea if you can handle it yourself, but if you're a tech specialist on duty responsible for the system, you have to try to solve it for yourself first. Rush checking logs and presentation service? It is better than previous options, but still may be ineffective. Most of the time, log records aren't helping when investigating performance issues. But wait, don't we have some methodology explicitly designed for this kind of issues? Let's try to solve the issue going step by step. So we start using the methodology. We will go step by step and I will make small conclusions after each step so that we can track our progress as we move through. So our first step is a problem statement. We calmed down a second level support engineer and started asking questions. Question numero uno. Why do you think we have a performance issue? Answer. We have complaints from users about long presentation loading. Okay, not much info, but now we know that there is a problem. It has a user impact, and it is critical as the ability of customers to view presentations is a core functionality of the system. So the company is losing money or will start to lose them soon. Second question. Do we had some recent changes in software, hardware, or load? Answer of SLS engineer. There was no hardware or load changes. I do not know about software. Okay, not much luck. We will have to look everywhere, but I recommend zero trust approach. If the SLS engineer tells you there were no changes, it does not mean there were no changes. It means that they may or may not change. There may exist some changes that SLS is not aware of. So keep your eyes open, as nothing can be ruled out just right now. Third question: can we express a problem in terms of metrics? Answer: our Grafana shows that response time on client raised from 100 milliseconds to 3 seconds for the 99th percentile. Okay, so now we have a baseline for the client, and it will help us to set up our acceptance criteria. Let us make the first conclusions after the problem statement. So, we indeed have a problem with loading presentations. We do not know if there were any software changes, and we should keep this info in our mind. The load has not changed, but response time raised. That implies that probably something had changed on our side and degraded performance. Either software, hardware, or configuration has changed. So this is not a load issue. For simplicity, let's set acceptance criteria as response time for the client should return to the previous level. So we know that we indeed have a problem, and we set our acceptance criteria. Let us move to the next step in methodology. Let's check all our services with the red method. Order of checks may vary, but I recommend the following data paths from the issue reported location down to the data route. Most of the time, it is the fastest way. So we check the presentation service. We observe an increased amount of errors on calling proxy service. We have some timeouts. We see that requests per second dramatically lowered on proxy service calls, and response time of proxy service increased dramatically. So it looks that the presentation service was failing because of the slow proxy service. These cascading issues are pretty common in microservice architecture when people forget about the circuit breaker pattern. So the following service is the proxy. The process here is the same. I deliberately copy-pasted the previous slide to show repetitive manner of checking services. Sometimes performance engineering is really boring. Once again, we see some issues on the next service in data path, user metrics service. We should check it out. User metrics service. We finally reached user metrics service, and looking at threat metrics on the database, we see the following. The number of errors on database writes majorly increased compared to historical data. Amount of transactions per second lowered significantly. And database time, response time also raised. Small conclusions. Database is a terminal service in our data path. All other services probably were failing because of it. We need to examine the system components of the DB service and find out what happened to it. We have an UC method, so we should apply it to our database. So, first of all, we have to identify resources on the target system. We have database application itself, network, disks, memory, file system, CPU. Let's iterate through the list of resources. Once again, order is not fixed. You can choose any ranking you like, but I prefer going from top components in user space to kernel space and hardware, because most issues arise at the user space level, at the very top. And results. Database has no errors. Average utilization is 90%. Database is saturated. We have 4,000 requests in queue. Moment of reflection. Wait, why is utilization 90% and the system is saturated? I said like 20 minutes ago that saturation arises when we fully utilize the resource. That is sneaky tooling that can fool you here. It is common to visualize utilization over some period of time instead of instant utilization. For example, if parking near your office is filled in the morning, parking utilization is 100%, and parking has definitely have some saturation. And your parking has a lot of free slots at midnight with the utilization of, let's say, 5%. Then we say that average utilization is 60% per day. And how much info does this give you about load spikes in the morning? Not much. So beware of this. Many engineers fall into this trap. If you see that utilization is less than 100% over some period of time, that does not mean that you do not have any saturation. You see method, database analysis conclusions. Okay, so now we know that failing component is the database application itself, and it is saturated. It does not have any errors. Remember that SLS told us that load from the client has not changed over time, and that really corresponds to historical data. It is easy to fall into cognitive BS and believe that DB has some bugs and performance degradation just happened without a reason. It's a great example of early blaming strategy. But let us reason about our findings. Does DB have any other clients? Yep, it does. It is a business intelligence service. If we do not find anything useful at the BI service, we will return to the database and examine other system components. Okay, we are looking at the BI service. So we check BI service metrics. They are fine. Okay, we have no errors. But when we compare metrics with historical data, we can see that service had periodic spikes of load at 3 a.m. out of business hours. But today's spike was at 3 p.m., just around the time SLS guy has called us. As we know, BI service schedules jobs to grab data from database and process it. Probably somebody changed the scheduler configuration and messed the job time. Checking with the configuration proves that, and now we know that somebody has changed scheduler job execution time to 3 p.m. right at the peak of business hours for our presentation service, and that probably caused additional load. So let's approach fixing issue. Hypothesis. We're sure that this configuration change at BI service caused additional load on database, and online transaction processing was endangered by online analytical requests processing. Pretty obvious hypothesis fix. Stop the job and revert destructive configuration changes. That should reduce load on database and decrease the response time for clients back to the baseline. So we apply according changes and monitor our services. We can see that metrics are back to typical values. We met our acceptance criteria and we can close the ticket. We respond to SLS with our investigation details and deploy a fix. And the final important step, we document our findings and report to our team leader or manager. Every production incident, including performance degradation, must be discussed, and your team should develop reasonable prevention actions. This is it. You earned your coffee. Together we resolved the performance issue, and it is time for us to recap the highlights of this talk. I have mentioned a lot of technical topics, but we have not concentrated our attention on them because this talk is not about technologies themselves. It is about growing an engineer in yourself. It is about developing structural and rational thinking. It is about abandoning your emotions and keeping your head cold. It is about bringing value to everything you do. It is about mindset. It is about how you perceive the world around you and yourself in this world. First of all, if you are an engineer, you have to develop business-oriented thinking. By saying this, I mean constantly reviewing your actions and asking yourself, is my current activity helps to grow the project or the company I work for? If the answer is no, then you should abandon this activity immediately and find something useful to do. The getting things done principle is fantastic, but it means nothing if you do dump tasks that do not help your business. This is business thinking I encourage you to cultivate in yourself. Your time is most valuable asset and you have to spend it wisely. There is popular expression, an engineer has to be lazy. Do not do things that you do not need to do. Do the most important things first. Maybe other tasks will die by themselves. Do things as simple as possible, but not the simpler. Plan your work, constantly optimize all of your activities. This methodology is a product of time management principles. When you need to complete something quick, you need a good plan and an attitude to keep to that plan. Performance engineering can bring a lot of fun, but the hard truth is that you should do it only when you need to, because it is challenging and time consuming. You need to know what to do when problem arises and crush it like a rock star. Use systematic or even scientific approach. Don't rush into unknown. Plan your activities, research unknowns, transform them into knowns. Follow the darkness and encourage knowledge expansion. Document your findings, document your systems, make your reasoning and actions clear and understandable for all. Engineer a sustainable world. Thank you. Now I'm ready to move to the QA session.
Hello. Thank you for
Hi.
a great speech. We all enjoyed it very, very much. Hope you do also.
Sure.
And I invited you and all our participants to the discussion table. Hope you will get a great conversation there and hope you will enjoy the rest of your day.
Thank you.